Hello and welcome to the video. This is a video with lots and lots of practical testing of motors and props, specifically to answer a couple of questions that I personally had and also to illustrate some of the pitfalls that people occasionally fall into. Now, I did a video a while ago on how I choose motors and props for fixed wing, and it's a very simple way that I do it. I figure out the weight of the model, how much thrust I want, and then I find the motor and prop combination that will give me that thrust at the best efficiency. And that's usually going to be lower kV motors with larger props. Now, lots and lots of people have very dearly held opinions of how you do this particular choosing. And if you have a way that works for you, brilliant, this probably isn't going to be the video for you. However, if you're relatively new into fixed wing, or you're kind of interested into how to read some of these tables, then hopefully this will illustrate how all this works. There's no substitute for practical testing when you're playing with individual motors and props, because the data in the tables is more of a guide. Individual props will create different effects with a specific motor. So I can have an APC 9x5, I can have a Aeronaut 9x5, I can have a no-name 9x5 prop, put them on the motor, run them and test them, and I will get completely different results. So you have to take some of the thrust data with a pinch of salt. So in this video, what I'd like to do is first of all say big thank you to Ben at 3DXR, because he was amazing at helping get all these products to kind of put on and do some testing. But the first thing is I want to see whether or not the thrust data that's in things like the T-motor tables, if we just jump on the computer. So here on the computer, this is one of the models that I really like. This is the AS2814 from T-motor. It's an equivalent motor to things like the Sunny Sky, but in my humble opinion, it seems to be built a little bit better. Now, there's a number of KVs that you can choose from. Hopefully, we're going to have different KVs. It's a heck of a jump from 1200 to 2000. Now, I was running the 1200 KV version. And if you zoom down, the really nice thing is you have all the thrust data here. So you can see the amount of throttle, the voltage that was used, whether it's 4S or whether it's 3S, because you'll notice here on the really big props, it goes from 15 odd volts even, down to 11 odd volts. But you also have then the amount of amperage it's pulling, and you have the thrust as well. So you can see here on a 10 by 5.5, we're going to get nearly 2 kilograms of thrust, and it's going to be pulling about 32 amps. If we go up an inch on the prop, we're going to go up to 36 amps, and we're going to pull another 210 odd grams of thrust as well. This is really good data, but I'm interested, these thrust numbers here, are they what you're going to get in real life? Now, I'll get onto some of the caveats in a minute, because none of the test equipment that I'm using, it has been calibrated. It's all hobby grade stuff. And you don't know the temperature and pressures and all those kind of different things. It does give you the fact in the data that it's an APC prop, but I'm going to try it with other props as well. Also, it's a static thrust test. It's on a bench, it isn't flying through the air. The thrust a prop will generate sat in still air versus when it's already traveling at 40 miles an hour is going to be different as well. The other thing I'm interested in is that at the moment I am running that model that I talked about with a 1200 kV version of the motor, and that 1200 kV version of the motor is doing okay, but I need a little bit more oomph. So if we look down here, that's the 900 kV version, there's the 1200 kV version. So I'm running it with kind of a 9 by 6, and it's going to be giving me about, according to this, 2 kilograms worth of thrust. Now that, for the model that I've got, is not bad. I can just about launch with that, but I would like a little bit more thrust. Now, the recommended motor for this particular model is that size of motor in 1400 kV. So got a couple of options here. I can either get rid of the 1200 and replace it with the 1400 and keep the same prop, or are there other more efficient, better options to give me more high-end thrust? And the last thing I want to test as part of this is there are a couple of pitfalls that a lot of pilots fall into. First of all is by putting a larger prop on, they think they're going to get more thrust. As we've already seen by a quick look at the data, putting a big prop on will make the motor pull more current. And while the T-motor's data is actually really good, it gives you several props. So in that instance, there is the opportunity to prop up and get more thrust if your ESC and power system can handle the additional requirements for the current and the wattage that it's going to pull. Then the other thing that I want to talk about is there's a common misconception that kV equals power, and going from a 1200 to a 1400 kV, all 1400 kV motors aren't the same. It has to be kind of the same size of motor for you to get an increase in power. If you get a smaller motor with 1400 kV, it isn't going to produce anywhere near that level of thrust. So let me run through a couple of caveats before we get really into the weeds in this, and hopefully some of this data will be interesting to you. Now, to be as fair as I can in the tests, both Ben and I were trying to do this reasonably scientifically. Again, none of the equipment that we're using is SI. It hasn't been calibrated. It's hobby grade stuff. So there is quite a variance of tolerance here on the numbers that we're getting. We are, however, using fully charged 5,000 milliamp hour high-end lipos for each of the pulls. That hopefully should mean that the voltage is more or less the same, so we can almost kind of take that out of the equation and just look at the current that's being drawn for the very simple efficiency calculation. I'm going to use Aeronaut props for all of the testing. I really like Aeronaut stuff here, and that happens to be the stuff that 3DXR has in stock. It also has a full range of APC. I just personally like the Aeronaut stuff better. It's going to be in the same position, in the same place. It's in indoors, so in terms of the pressure and the temperature and stuff, that's going to be constant throughout the testing too. The idea is we're going to run it up, go to maximum thrust, make a note of what that is and what the current draw is, and then we can see and compare the maximum thrust with what the thrust is in those tables we've just looked at. And then also go in 500 gram increments, so 500 grams a kilogram, 1.5 kilogram, 2 kilograms of thrust, and actually plot out the current for those 2 or 3 data points to give us an idea of how that curve looks too. So to actually do the testing, what we did was bolt it down. I'm using this thrust measuring device. This is actually one that I got from Banggood. I'll put a link down below. Occasionally they struggle to keep these in stock. And then what I'm using is a watt meter, and we're using a servo checker to provide the power. And again, the ESC has been calibrated, so when we're 100%, it is 100%, and it's going to be consistent across all the tests too. Now, the first thing I wanted to look at was on this AS2814 motor, there are a number of props listed. So what I asked Ben to do was to get the 3 props that are closest to the thrust data that's listed. So that's 11 by 5 inch prop, a 10 by 5 and a 10.6, and pop them on and do each of the runs. So the first test was to look at these AS2814 motors. Again, I was running a 1200. The option would be to go to a 1400 version. Probably have to go to a Sunny Sky motor at the moment, unless I went for a different KV. But there's also the option to go down and actually use a bigger prop to get more thrust. So here's the results. Now the amp draw is along the bottom. So obviously the further to the left hand side, the origin of the graph, the better, because that's the lower amp draw, and then the thrust is there on the left hand side. Each of the dots is the data point. Now the first one to look at here is the blue one, the top one, that has the little diamond shapes as the data points, and you can see that they all start kind of similar, and as you go up through the 1.5 kilogram, 2 kilogram, and then 2.5 kilogram, it actually is reasonably linear, but you do find that most of the traces have this gentle flattening out, and that's to be expected. As the prop increases, the efficiency drops a little bit. But the cool thing is, the maximum thrust that we got at the 11 by 5 inch prop was a whopping 2,927 grams. So that's a stone's throw away from 3 kilograms of thrust out the 11 by 5 inch prop. At that amount of thrust, it was pulling 52 amps. If we compare that with the same motor on a 10 by 5 inch prop, and that is the data set, the red data set with the square data points, maximum thrust of that was 2,545 grams, pulling 44 amps. If we add a 10 by 6 prop, then we get some really interesting results. On this one, the maximum thrust was bang on 2,500 grams or 2.5 kilograms, but it was pulling 50 amps. So this is one of those kind of weird things, and occasionally you do find this, and this is why practical testing can be really good. This particular prop and motor setup is not particularly excited about a 10x6 prop, but the 10x5 prop and the 11x5 prop, again these are both aeronaut props, I'll put links to everything we're using down below, work really well. But by using an 11x5 inch prop, we are getting significantly higher levels of thrust. If you compare the 11x5 prop, the blue trace with the diamond data points, to the green trace by the 10.6 prop, which is the least efficient out the bunch, then you can see that even at similar amp draws, we're getting significantly more thrust out the 11x5 inch prop. So that is the prop that I would go for. In fact, if you compare the thrust levels at the 2.5 kilogram level, for the 11x6 inch prop, it is pulling about 44 amps, whereas on the 10.6 prop, it is pulling 50 amps. So 6 amps less for the same amount of thrust. If we do the plots of those same pulls with the grams per amp at the bottom, so again the thrust is on the left hand side, it's the amount of grams per amp at the bottom as kind of just a way to show the efficiency. What we want ideally is we want the trace to be as far to the right this time as we possibly can. You can see much more clearly in this particular way of looking at the data that the 11x5 inch prop, with the exception of the pull at 2.5 kilograms, is by far the most efficient out of all of the bunch. The worst is the 10x6 prop, and definitely that particular prop and motor is a combination I wouldn't use. Now the next test I did was to test the AS2814 1200 kV motor, and that's the one that I have been using on the model with a 9x5 and a 10x5 inch prop. Both of those are in the data points in the T motor stuff, well, close to, slightly different prop pitches, but it does say that we can absolutely prop up on that motor, and that would be an option for me to do more thrust. These are the two plots, again amps across along the bottom, thrust along the top. So ideally we want a trace that is further to the left than to the right, because that is probably going to be more efficient. And this time we can see that the 10x5 inch prop gives us much more maximum thrust. So at full tilt, the 10x5 inch prop is giving us a 3 kilogram thrust, but it's using a whopping 60.5 amps to do it. Compared to the 9x5 inch prop on the same motor, it's giving us 2,550 grams of thrust, but it's using 50 amps. Now there is a slightly weird data point here at the 2 kilogram level for the 9x5 inch prop, but you can see here that we definitely can get a lot more thrust by propping up. I would have got another 500 grams worth of thrust, but it will be consuming an extra 10.5 amps to do it. Now the issue for me is I can't prop up to a 10x5 inch prop in the setup on my model because it's a 55 amp ESC. Although it will support small amounts of higher current for limited amounts of time, if I want to fly it flat out for longer periods, that ESC is not going to work. So this wasn't an option for me, but if I'd had a bigger ESC, it might have been. If we compare those two traces, again looking at the grams per amp to give us a rough fag packet sketch of the efficiency, again it's really clear on this particular way of looking at the data. The blue line, that we want it the further right as we can, we want the most grams per amp, that's the most efficient, and the 10x5 inch prop here is absolutely working the best. The 9x5 inch prop is actually not a great option. So let's look at some of those data points with my specific scenario in mind. So I am right now using an AS2814 12,000 kV motor with, it's actually a 9x6 inch prop in my particular instance, it's a folding prop, but we've got a 9x5 inch prop in here. That is the blue line, that's the one with the data points that look like little diamonds. You can see here that that is the one on the right. So it's consuming the most amps for the thrust that it's creating. If we compare that with the other two data points, with a lower kV motor, that's the 1050 kV motor we looked at the start on 11 by 5 inch prop, that actually does really well. That's really efficient. It's giving a really high level of thrust, and it's also doing it at the lowest amount of amps. The next best option is that one that we've just looked at, where propping up to a 10 by 5 inch prop will take it to a whopping 60.5 amps, which is just a little bit above where I need to be, but it is going to produce 3 kilograms of thrust. However, using that AS2814, the 1050 kV motor, the leftmost red line with the data points, you can see here that the amount of amps that's being drawn to give pretty much the same amount of thrust is significantly lower using a 1050 kV motor with an 11 by 5 prop than using a 1200 kV motor with the 10 by 5 inch prop. And that is going to result in lower heat. It's going to result in longer flight times. So that is what I've decided I'm going to put on the model. I'm actually not going to increase the kV, I'm going to decrease the kV but increase the size of the prop because it's going to give me the most efficient flight. Let's have a little quick talk about getting some more thrust. So here's a number of different motors all tested. Again, the one that we're all comparing it to is the one at the top, which is the AS2814 1200 kV on the 9 by 5 inch prop. That's the one we've looked at quite a few times. That's the one that I've been using on the model so far. If we compare that with two other motors of higher kV on the same 9 by 5 inch prop, you can actually see that we don't get a significant increase in the amount of thrust, but we do get a little bit more amp draw. Now, I personally think the data point on the 9 by 5 inch prop for the AS2814 1200 kV, the blue line at the 2000 kilogram pull, there's a bit of an aberration in that data point. I think we would definitely see that 1200 kV 9 by 5 inch prop is still the most efficient out of all of them. But what this graph clearly shows is that if I wanted to add more kV into the model, then using a motor of the same size, a 2814 motor, would be what I'd have to do. Going to a smaller motor with a higher kV isn't actually going to give me that much more thrust. So don't fall into that trap. If you need more kV, then ideally pick a motor of the same size with a higher kV rating. But if you want more efficiency, you might want to do what I'm doing here, which is you go for a lower kV, but you add a bigger prop. So how do the maximums compare that we got in the testing that we did with the maximums that are actually in the data sets? So if we look at the T-motor stuff, that AS2814 1050 kV motor with the 3 different props, you can see that we were getting consistently much higher thrusts with the testing that we did. And again, caveat, none of this is scientific equipment. We were getting consistently higher pulls than the data in the table. So from that, I can take away that the thrust data in the T-motor tables, particularly with the aeronaut props, in static testing, you are going to get more thrust, and that's really good to know. But the question it's raised for me is, how are they actually testing the props in their environment to get that table data? Maybe it's something to do with the fact they're using APC, I'm using aeronauts. That will make a difference, but I'm not sure by how much. But it would be interesting to know a little bit more from T-motor about how they do their thrust testing. If anyone from T-motor is watching, I'd love to talk to you about that. Maybe that might be another video. So with that practical testing done, and thank you for sticking with it. I know that's lots of data and graphs, and not a lot of people kind of use that kind of way of consuming information all the time. Let me kind of summarize it for you. The static tests for all of the thrust that we played with for the motor and prop combos were significantly more than the stuff in the T-motors tables. So the stuff in the T-motors tables, you can be pretty confident that you're going to get in a real world example, particularly a static thrust test. If you want more efficiency, then the rule of thumb appears to apply. lower kV with larger props will typically give you a more efficient thrust than a higher kV motor with smaller props. But that's reasonably common knowledge, but hopefully you've seen that from the data. Also, hopefully you've seen that having higher kV doesn't necessarily equal a lot more thrust. It has to be a higher kV in a similar size of motor. Small motors with higher kV, you can't just replace a massive, great big motor and with a little teeny weeny motor with a different kV and expect the little teeny weeny motor to deliver more thrust. It kind of doesn't work like that. And putting different props on a motor will produce different levels of thrust and different levels of efficiency. So be aware of that. Nice that T-Motor actually published that data. I wish more motor manufacturers did it. It makes it an awful lot easier to see the thrust that you're going to get and to do that basic calculation that I do. It's the weight of the model, figure out how much thrust I want, and then I can look it up on a table and buy that motor and prop. But it also is handy if you are in that situation, you need to prop up, being able to look at that motor combination, motor and prop combo with the battery that you've got in the thrust tables and figure out whether that's even possible. But what this has really proven to me is that there is no substitute if you want to play with this stuff to invest in a thrust meter and a watt meter and just run the data yourself. It is particularly handy if you have a bunch of old motors in the spares bin and you're not exactly sure how they're going to run. Actually running them like this is a great way to do it. Start them on the smaller prop and build up. Watch particularly for heat when you're testing. All of the motors were just slightly warm at the end of this. We could have probably continued to prop up well beyond what the recommended figures were for T-Motor, and it would have started to get hotter and hotter. But we were kind of just comparing at this point to just compare the different results with the table and real world, and also for me answer the question as what's my best option moving from the 1200 kV 2814 that I'm currently using onto something else. And I'm going to go for the efficient option rather than go for a 2814 1400 kV motor with the same 9x6 inch prop. Now, if this has been interesting to you, and for me it's prompted a ton of other questions, then if you want to kind of pop them down below, maybe this can become the start of a little series where we delve into some of the more detailed minutiae about how motors and props and thrust and efficiency and all that stuff go together. Props are essentially two little wings, and the way they generate the thrust is incredibly complicated from an aerodynamic point of view. Things like, the pitch makes a difference, things like the aerofoil design, whether or not it's a static or folder, how much difference is there between an APC and a other brand of prop, things like an aeronaut. If you're interested in kind of exploring some of that, if you can pop the things that you want tested down below, next time I can talk Ben into setting up this rig, we can do some more of the testing and come back with some of the results. So thanks for sticking with it. I know it's a slightly more technical one this time, but hopefully for those of you where this is an area of interest, that has potentially answered a lot of questions. It did for me, but it's probably raised just as many. Thank you for spending your time today watching that video. You can find me in all the usual places on social media, and if you're trying to learn about a subject, then check out the playlist. All of my videos are organized into easy to follow playlists that if you're trying to learn a topic will take you from the basics right the way through to some pretty advanced stuff.